Welcome back. Here last we did the summing amplifier, and then with the summing amplifier what we then do is I said I'm gonna come back and look at a special case. All right, now we manipulate this summing amplifier and we do something special with it. I may be forgetting to put the headlines here, but I say it, so hopefully it will think. What I'm going to look at here is what we call the digital to analog converter using the summing amplifier. Okay, using the summing amplifier, there is the R to R method, and then there's the summing using the summing amplifier. Okay, how does this work? Let's take a simple scenario. I will take a 4 input stage. I said I'm going to need a 4 input stage. Now what I'll do is I'll have my 4 inputs. Might be a bit of a long session. Remember to like. If you like what we're doing, it helps us, it motivates us. It also, let's have V1, V2, V3, V4. Now we have R1, R2, R3, R4. Now all we're going to do is these ones must join together, catch-offs, because they must sum up. They must join together. Feed the op-amp. I don't want to feed it there for a simple reason that, well, I can if I really give it distance and then do this. This is our inverting configuration, so it's going in through the negative, the inverting, and then we have our feedback. There is one thing I need to mention though. Remember, we said typically this will be about a meg. So our argument, a mega ohms impedance. So our argument that this is a high amplifier simply suggests that this one has to be low compared to that. The best practice will be more than 10 times. This should be the difference in impedance here between the op amp and that should be in excess of 10 times at least. 10 times is not good enough for me, but that is not as bad as when it's now close to it, because then that argument that the current will be rejected, it won't make sense, it won't hold anymore. So what we are saying is to not saturate our op amp, we need to have a relatively lower feedback resistance. This feedback resistor must be relatively low compared to the input impedance of the op amp. Otherwise, if it's on a similar range, then obviously our argument that the op amp should reject the other current will not make, all the current should not make, would not make sense. So this should be substantially bigger than that RF to avoid overloading or some current forcing through the op amp itself. All right, because remember, the whole idea is the op amp must reject the current and push it through RF. That is the whole point. That's why it's designed to have high impedance, so it rejects our input. All right, so if however the two are likely in the same range, then obviously now there will be sharing of currents, so this is why the op amp has to have significantly higher impedance. All right, so now RF typically cannot be 1 meg if this has an input impedance of 1 meg. All right, it should be way less. All right, so now I will take an example where our RF, so let's take an example. V out, remember, is given by the formula. It's an inverting configuration, so it's minus RF by current 1 by current 2 by current 3, whatever, because it's remember, this is essentially V out, which is R times I. All right, but then the I is the sum of all those. Let's call that I1, I2, I3 and I4. So here I4. So this is the sum of all the currents here. All this current. This current is, according to Kirchhoff, they are coming to a node and then he is leaving the node. So obviously, now you would say yes, there's a current there and the current there, but because this rejects, the current there is quite insignificant, and all our current is basically, well, all our current is a bit of abusing our terms, but the bulk of our current is pushed through RF. So essentially there's very little difference between that current there and the current through RF. So this here is I total. With that little loss there, but it's only a sample, so it's only a sample. It's such a tiny current that it really doesn't amount to much. All right, so this here should be our output is supposed to be RF times I total, but then I total is the sum of this current, which is the same as V1 over R1. That's the one current, plus the second current, plus the third current, plus the fourth current in this case. Why 4? Because there is 4 inputs to what? Let's say it's 8421. There is 4 inputs. We need 4 inputs to the what? Remember, this is digital to analog, right? So it has to be a what? A digital signal that will give us a what? An equivalent analog value. All right. So now this here is going to be what? It's going to be what did I say here? R4 already. Rushing ahead of ourselves over R4. All right, this V3 over R3, and then obviously that whole voltage there. Let's have a scenario where our RF is equal to, as a random example, theoretical example, 20K. Okay, let's have R1. Let's have R1. Let R1 be equal to, let's say 100K. 100 kilo. So look, it's 100K. That's why I normally prefer to R2 is equal to 50K. Look how this is half of that. And then R3 is half of half, which is a quarter. So you can see this is 1 half, 1 over 4, which is equal to 25. Obviously, 1 over 4, 1 over 8. 8 there will be R4 is equal to, so you can hear the numbers, 1 half, quarter, 8. So you can see the 8421 there. All right, this is 25K, and that there is what? Is 12.5K. All right, that's our scenario there. Let's see what happens now. Let's say now let V1, or let V1 be equal to V2 be equal to V3 be equal to V4. Okay, and then they are all equal to 5 volts. Why? Digital electronics, our high is 5 volts. All right, so now, okay, I need to close this. How did you get here? All right, let's exit this. Cancel. What am I doing here? I don't see how I got here. Let's go back down. Okay, that's the first time that was accidental. I think it's when you press this here by accident. All right, so okay, we learn as we go. This software. All right, so now I hope this is still visible. V1 is equal to V2 is equal to V3 is equal to V4. All these voltages are equal, and they are all our digital signal of what? Of I want to say is equal to 5 volts. I should have just said 5 volts, all of them, right? That looks like a 3. Okay, now it's 5. Now let's do our math here. Let's say V1, let's say we have, what is going to be our V out in this particular case? In this particular case, therefore, for given values, this is the general case for 4 resistors, but for given values, V out is equal to minus 20K by, this is V1 is 5, all of them are 5, over that one is 100k, and then plus V2 is 5, all of them are 5, that is 50k, plus all of them are 5, but that is 25k, plus all of them are 5, and that is 12.5k. Okay, so here this is going to be equal to minus, you can see the k cancels all the k's there. This here will do that, kill all the k's. Okay, what do we then have? 20 times 5 over, that will be minus, this one is 1 because it's 100 over 100. That one there is 100 over 50 plus 2. That is 100, 20 times 5, 100 over that. That will be plus 4. You can see I'm adding 8. What call this? 1, 2, 4, and obviously that is 8. Okay, because this is 100 divided by 12.5, which is obviously 2 times that. That was 4. This should be 8. So you can see we've got minus 15 volts. So let's see. But how does this translate to our digital? This is just us doing our electronics. Let's see how this translates to a digital scenario. Let's suppose that we had one common input, which is 5, and then we did this. We had switches there, and that will be A, B, C, D. All right, now so now they are all wired to our digital input of 5 volts. Now you can see, I don't like this one. It's somehow I don't like it. It does not show our proper switch shape. All right, now you can see now, for us to have all these voltages, we must close 1, 2, 3, 4. Then we have what we have here. All right, so now let's suppose now, so that would mean, if you look at the switches, that would mean A, B, C, and D, and you can see that okay, I think I've placed it the other way around. The A for the 8 is the one, the smallest one. So let me rather rename them. I've named them the wrong way around. This is A. If we call this A, that B, that C, and that D. And now when you close all these switches 1, 1, 1, 1, you see that when you close all these switches, our output voltage is okay, ignoring the 15, but yes, 1, 1, 1 is 15. What have we done here? Through the switches, which is now the digital electronics, now our switches, so this can be 0 or 1. So now let's go and say, if we didn't have, if C was open, if we left C open and we close D, B, and A, it would mean that this one here will be 0, meaning that we don't have 5 volts there, we have 0 volts there. If we have 0 volts, that's going to give us 0 here. And what do we have? We would have there 11 volts. We would have 11, no, not 11. What they do, this one here, oh, this is A, B, I closed the C, so I've looked at the wrong one. This is the C, yes, this is the C. Remember, this is, let's clarify this, the biggest one is the smallest one. Our R1 is the 100K, so this here is the D, that there is the C, that is the B, and that is the A. So now, when we say C is 0, it means that part there becomes 0, that part is 0, so we've got 8 plus 4 plus 1, which is what? Which is obviously our 13 volts. It would give us our 13 volts. So what I want to see, what I want to show here is we want to show how we can use our summing amplifier to give us the what? The digital to analog converter. So I hope that was clear. I hope it was not much of a thing. So what was the idea here? This here is been us doing the summing amplifier as we did in our previous class. So now this is everything. This is the general output for that. But now if we make this relation, the voltage a digital pulse, and we throw them through switches, and then we have these being from the biggest one to the smallest one, we have them having a factor of 2. Remember, digital electronics loves the factor of 2. It's based on 2, it's base 2. So now, if we do that, then we are going to find ourselves converting switches into analog values. All right, we're going to find ourselves switching digital values into analog values. All right, because remember, switches are our digital inputs. All right, so I hope this makes life clear. What I'm going to come and again, I'm not happy, I'm not done. I'm gonna come back again and do a digital analog to analog converter, which is going to basically do what? Which is going to basically do the what you call them? Let's remember them nicely. The BCDs, all right, the BCDs, all right, the binary coded decimals. I want to have a situation where this gives me a certain only up to 9. The next one gives me another set that will give me up to 9, so that I can have what? I can have 8421, 8421, 8421, but they are each giving me what? That factor of 10, the units, the tens, the hundreds, and so on and so forth. So for now, I hope this is clear enough. I hope it clarifies how our subjects are so related. Our subjects are so related. When our students do this in electronics, those who don't who don't go on and do digital electronics as well, they do not see how these two things actually what they are learning there is actually being very useful in another aspect of life. Our school is interconnected. All right, then I hope you had fun. If you did, show us that you like it, like our work, and then encourage us to come back and give you some more. And also keep yourself abreast, keep yourselves reminded all the time how the moment you drop a video, you'll be the first to know how to do that. Simply subscribe. And with that, I hope you had fun. We tried to, and it was indeed a bit of fun. Thank you.